Thank you, everyone, for being so flexible uh, with your time here and the modality that we're gonna do this final lecture for repeated measures ANOVA in. This is not what I had planned, but I think this is probably the safest way for everybody to move forward. Um, we do have a chat function available. If you have questions coming up, you can always post them on the chat. Or you could just unmute and start talking, um, and we'll we'll answer them as they come up. As you might recall, we finished off our lecture on Tuesday with a write-up of our data analysis on the days of the week and their effects on people's positive mood. Um, and today we're going to talk about some special assumptions that we have for repeated measures ANOVA that are a little different than what you're going to be encountering in one-way ANOVA. And then we'll pull up an SPSS file. Let me just show you where I'm at here. So the PowerPoint slides that I'm on right now, you can find from Tuesday's lecture. And then the rest of the materials, really all you need to do is pull up the ELF data, and then this updated Word document. But that's going to come here in just a little bit. Uh, okay. So back to special assumptions of repeated measures ANOVA. The first thing that I'd like to talk about is subjects variance. This is that um, problem that I told you to ignore, to not even worry about. It might become important for analyses that you learn later in life. But for right now, I just want you to know what this is. So what's subjects variance? So let's say that we've got our next door neighbors, same street, and the next city over neighbors. But let's say that each of these is a person that you track throughout the study. Okay. So instead of being a between subjects design like we did with the one-way ANOVA, here you rate everybody. You rate your next door neighbor, your same street, next city over. So this brings it into the realm of repeated measures ANOVA. So we've got a bunch of individual ratings and we calculate each person's mean score across all conditions. So let's say that this first person here is represented by these three dots. So as you can see, they've gotten scores for next door, same street, next city. And this gold colored dot off to the side is their mean score. Okay. And we do this for everybody. Okay. Now there is a grand mean of all the scores in the data. And what we do is we look at how these average scores in gold, averaging across all of the conditions, vary around this grand mean. Okay, so this is what subjects variance is. And it kind of makes sense when you think about it, right? We've got an average score of all the times you've repeated this measure, and how much does your average vary around the grand average? Right, so that's essentially what we're looking at here. So subjects variance is calculated as, again, how much we vary around, our average scores vary around the grand mean. And SPSS gives you an output that looks something like this here. It's called test of between subjects effects, and this is your subjects variability. We just ignore this, but I want you to know it's there. It's packed in, and it might have some meaning later in life. Maybe not even later in life. Maybe it might have some meaning to you later in this program that you're in. But for now and for this class, just ignore it. No big deal. We're also familiar with a concept called homogeneity of variance, which we've encountered many times before. Um, we talk about this as homoscedasticity when we have a continuous independent variable. Um, and in repeated measures ANOVA, it looks a little bit different. So again, let's say that these are individuals across time. So here we've got this person rating their next door neighbor, same person rating a same street neighbor, and so on and so forth down to the next city. Okay. Right. So homogeneity of variance in a between subjects design would say this is a problem. Okay, this one group's variance is wider than the other groups, and that violates an assumption of one-way ANOVA. Okay. So we've been over this before. We test that with Levine's test. Uh, Here we use a parallel test of an assumption called sphericity. Sphericity. So here we look at paired differences, paired difference scores, and we want to know if these difference variances are equal. So let's see a graphic of what this looks like. These are all difference scores, right? You take each individual and calculate the difference between next door and same street. Okay. So this one, this difference is pretty big, and this difference is pretty small. Okay. And what we want to do is we want to calculate the variance of these differences. SPSS does this all for you. It takes the variance of these differences. So you're going to have some kind of like difference average. Um, and it calculates, okay, this one's pretty far from whatever that average is, I'm guessing, because it's the largest difference. This one's probably close to what we're looking at here. And then it says, okay, are these differences, the variance around them, the same as these difference variances? Now, this set of differences, its variance is probably close to zero. Look at that. There's no change at all. So, what you're looking at here is probably a clear violation of the assumption of sphericity. Here, these differences vary a lot more than these differences. So that's what it's looking at here. And then there's a third set of differences that we can look at. It actually takes all of the different comparisons, like here. Okay. Okay. So it takes each of these difference variances. Here we end up with three and compares them to each other. Now, the one thing to note is although I've said that you really only have to have uh, two groups to do a repeated measures ANOVA, you can't assess sphericity with only two levels of the independent variable. The reason why is there's only one set of difference variances between one group and the other group. How we doing, everybody? And the test that we use for this is called Mockley's test of sphericity. And we'll talk about how to report that um, here when we get into SPSS. So if all you got right now is that sphericity is kind of like homogeneity of variance and homoscedasticity, you're in pretty good shape. Okay, just another thing that we have to test and check for along the way. And, and you need at least three levels to test it. We've already talked about that. We end up getting an output that looks like this in SPSS. I tend to report, oops, sorry, go back, Dan. I tend to report the chi-square value instead of Mauchly's W. And then, depending on the result, if it's significant, we have a problem. That means that our difference variances are heterogeneous, different from each other. But here, this would indicate, okay, we've got no problem at all. We're doing okay, 0.750. So more on what to do if it's significant later. Okay. But we'll end up using some of this information over here under the epsilon column. So hang tight for that. If you don't violate the assumption of sphericity, you end up using these two rows. I'll say sphericity assumed. I had a student in one of my undergrad classes one time think that that said sphincter instead of sphericity, and then announced that to the whole class, which was kind of funny. Now, I mean, everybody gets a little immature about this because there's dozens of sphincter muscles in the body. You're just thinking about one of them right now. So that's on you if that's where your mind went. And then in other circumstances, if we do violate, you're either going to use something called the greenhouse geyser rose or the Heinfeld rose. Okay, so you're going to have a choice on that. And when we get into the SPSS file, we'll see that choice in action. How we doing, everybody? So, just like Jedis and Siths, we always return. Okay, I'm probably like somewhere between a Jedi and Sith, I think. And Kayla, you'll learn more about that sometime down the road when you finally sit down and watch Star Wars. Uh,
Don't say that too loud. He's home. He's gonna hear.
Good.
He's gonna make me watch Star Wars.
Yep. Um, that's good. You should. So we've got a bunch of special types of contrasts that we used in repeated measures designs um, that can be really helpful to us. And this is a big part of your eighth assignment, which is due when we get back from break. Um, so, sorry, I got to sneeze. Gross. Okay. So we know all about planned contrast. We've used effects coding before, and we've used Helmert before. And essentially, we use contrast codes to tell us something about patterns of data that might exist. It's a special way of stacking the deck so that you can see differences, if they exist, that you predict. In my opinion, contrasts are more hypothesis driven, and post hoc tests like the Tukey or Bonferroni, whatever you want to use, those are more exploratory if you don't know what your hypotheses are going to be. So SPSS has dozens of contrasts that you can use. And I'm going to show you one that's used in repeated measures designs a lot, and then we're going to actually look at a different one in SPSS today. One thing to keep in mind um, is that in the assignment, I quite literally describe to you what that contrast is doing. It tells you what's being compared and how it's being compared. So you're going to have to read for detail there. I don't think that we have time to cover every single contrast, but if all you know is that these contrasts are making comparisons in some certain way, you are good to go. So let's look at a special case of contrasts, and these are really handy in repeated measures designs because often in repeated measures designs, we are looking at things like time as an effect. Um, right. So maybe you're tracking people over time in uh, some kind of IO type setting, and you can look at their changes to an intervention. Um, Maybe you are, studying how people's empathy declines over the course of a study session, right? And you can model, time as the number of times that they've done a certain thing, right? They've got this task in front of them. Maybe you're working with folks out in the field and, you're providing some interventions to older adults with dementia, and you can see the effects of an intervention that you're giving them over time. There's a lot of different ways to think about this, and there's other contexts too than just time. So, like for example, drug dosage. We can look at these different shapes. These shapes are called polynomials, and they are really useful for any kind of repeated design. Um, my hope is always that I get a linear relation because that's the easiest to explain, but life doesn't always work out that way. Um, Again, you don't need to write all this down, but this just shows you that they are orthogonal. You can look at these in the way of basically how many humps are there in the line that you're drawing. For linear, there are none. Quadratic, there's one. Cubic, there's two. Quartic, and it goes on and up to infinity. The number of different parameters that you can use. So basically, what we're doing is we're creating codes that make a shape over a factor that is probably ordinal. Ordinal, like time, the order in which you saw different stimuli on a computer, um, the day in which you measured this person, say that they're doing like some kind of Montessori training in a home for folks. There's a lot of different ways you can look at it. So again, these are useful um, contrast to use when the variables or ordinal, like time or dosage. Um, and technically, it's going to be appropriate for the example that we're we're using today, like day of the week, right? Um, so instead of doing post hoc tests, we could have done a polynomial and found a relationship between the variables, what it might look like. We could even go back and check that out. Let's go back to those scores real quick. Um, I mean, to me, it almost looks like it dips down and then pops back up. Oh, screen sharing has stopped. You all can't see what I'm showing. Okay. Thank you so much. When you look at the means here, you can see that they dip down toward Wednesday and then ramp back up toward Thursday and Friday. Almost like it's a quadratic relationship. It looks like an inverted U. Okay. Maybe not perfect, because Monday's a little lower than Tuesday, but most likely this relationship, if you can picture these means on a graph, would look something like, I don't know, maybe like this, but if it were inverted, or maybe even a cubic relationship. Um, so the way that this looks in SPSS is it will give you multiple polynomials in a table called contrasts. So here you can see that neither of them are significant, which is not what we would hope to find, but sometimes it works out that way. But when you're analyzing this and interpreting it, you take the most complex polynomial that's significant, statistically significant, and that is your best model for the data. So even if, let's say, linear contrast was significant, if the quadratic contrast was significant too, we'd go with the quadratic. We would completely ignore the linear contrast, um, because that's the best uh, model for our data. Let me go back a couple slides here. So, how would we interpret that? Well, we would simply say it's a quadratic relationship, and you would go look at the means and see how they're shaped and just explain it that way. Right? So, uh, the way that this would look is, people decline in their positive mood uh, during the week, and then they increase toward the end of the week. So, hump day is called hump day for a reason. You got to get over that hump. How we doing, everybody?
Can you explain again why quad, or what did you say, the strongest proximity, quadratic versus linear? Can you explain that again? How the
Yeah,
significant,
yeah. So basically, it's a great question. Yeah, so I'm looking at the p-values here, and you might end up with multiple significant effects. Um, to make life easier on your reader and life easier on yourself, you take the most complex polynomial. So here, this one's quadratic. Let's say if it were significant, it's not, but let's say if it were, we would take that one. But if linear was the only one that was significant, we would use that and ignore quadratic. So as they go down the list here, they become more and more complex um, in their explanation, right? It's like the opposite of parsimony, right? Um, so the more and more complex you get with it, if that one's significant, that's the one that you want to report.
because that significance indicates a stronger relationship. Is that correct?
Um,
Or stronger effect of the it
I
varies.
I I wouldn't say stronger, right? Because you might end up with a p-value, whoops, go back, at like 0.001 here. But if this one's at 0.05, that's significant. This effect is much stronger, but this one would be the better at model of the data because it's statistically significant, right? So, um, again, I know that's kind of a cruddy way of thinking about it, but that's how we treat these. So you're not necessarily going for the stronger model. You're just looking for the most complex one that's significant. Okay. What other questions do we have, friends? So I would like to move to um, our SPSS data. Um, this is not data that I made up, even though it probably seems like that when you first glance at it. This is data that a guy named Andy Field made up. Um, and the time of year in which I like to cover this usually maps up to like well with like your belief in elves and things like that. So um, uh, this is a data set that's full of elves. Andy Field even named them, and and I think I've left that in the data for you. Let me see. Let's go over to the data here. Or did he take them out? I think I took them out. Okay. Yeah. Okay. Can you all see the data here? Yeah. Okay. So let's say in this study, we wanted to give um, elves a test in which we measured their present delivery time. And if you know anything about elves, they love to drink. Kind of like when Will asked, "What do you all do for alcohol?" Elves do sherry. They really love sherry. It's the best. Um, and we wanted to do an internal study to see the effects of the number of sherries that the elves drink on their present delivery time. Okay, so smaller times are better. We don't want any delays in these presents. Okay, so you can see here that each of these elves, look at elf number 9, um, has done this test 5 times. And before the first test, they drank 1 sherry. Before the second test, they drank two, and so on. For the fourth test, they drank four. Okay, and then before the fifth test, they drank five. Lots and lots of sherries for our elves here. Okay, now, I know you're looking at this going, okay, well, the number of sherries, that's at a very minimum ordinal. So maybe we should use a polynomial contrast here. Um, we won't do that first. I'm going to show you how to use something called a repeated contrast, and then we'll go back through and run a polynomial and see what that looks like too. Um, so we want to we want to find out, okay, is there a cutoff for these elves when it's like, all right, enough's enough. You can't you can't have any more. You're you're really you're really going to mess up this present delivery time. Yeah. So on, and it might be helpful for you to uh, pull this stuff up on your computer as you're working along, but um, I've actually got a write-up already, and I'm going to go through each of the outputs and talk about how this is going to help us with decision making along the way and how we get our reports that you see up here. That looks like a really long report to figure out if alcohol consumption affects our elves. Okay. So let's go back to our SPSS data and run an analysis. Um, Does anybody need like a minute or so to make sure they get their data up? You could just raise a hand on the
Yes,
screen.
please.
Yeah. Okay. Yeah. And I can pause the recording, but yeah, the recording has resumed. Um, so here again, you got to think about the way that your data are organized when you run SPSS. The one thing that always helps me is one row equals one person, or in this case, one elf. Um, okay, so one row to rule them all, one row to find them. Okay. And what we're going to do first is we're going to go up to Analyze and then to General Linear Model and Repeated Measures. Um, is this showing up in front of the screen? Do you all see where I'm clicking? Okay. The reason I ask is Macs and PCs are different. You actually have to present it in a different way on Macs, but I'm on a PC, so I think we're good. Zoom is such a weird thing. I'll click on repeated measures. And then the first thing that comes up is this little box that says repeated measures define factors. Okay, so we've got only one factor in this variable here, or sorry, in this data here, and that factor is Sherry. And we have 5 levels of it. Okay. And I'm going to click add, and it adds it in. So I name this Sherry and change the number of levels to 5 and just added that in. I don't even know what Sherry is. I feel like that's a song from the Four Seasons. Who has somebody who can sing high enough to sound like an elf, I think. Um, you know. All right, I'm going to click define, and then we get a new dialog box that pops up. The way that we do this is we move over each of our levels of the independent variable. You could do it one at a time, or you could do it, all together, just highlight them all and then move them over. And then the first thing that we're going to do after that is go up to contrast. And right now it's set to polynomial. So, I mean, if we wanted to do polynomial, it's already set to it. That's cool. We can give it a go. But instead, I want us to change this to repeated and then hit continue. Okay. Sometimes it doesn't take for whatever reason. Okay, yeah, we're going to do a repeated contrast. It took just fine there. Okay. Right. And you can see there's a whole bunch of different types. We've got difference, Helmer, repeated, simple, so on and so forth. Whoops. Sorry about that, everybody. Okay. You don't have to do this, but I like to see what my data look like, especially if I'm ever using polynomials. Um, can everybody see this dialog box that says profile plots? Okay. I'm going to move this to the horizontal axis and hit add. Jacqueline gave a thumbs up. Cool. Okay. Wait, do they have one that flips you off? It's like Ah.
Sorry. I was just trying to say that I could see what you're saying. Sorry.
No, that's I appreciate it. I knew that's what you meant. Uh, yeah, I'm trying to look through the reactions here to see do they have a middle finger. This is for another time. The world that we live in now. Uh, yeah, and I can do the little hardy eye face. Okay. Um, I'm going to keep this as a line graph. Generally speaking, I think when we have uh, like separate groupings, like in one way ANOVA, we want to use a bar chart, but let's use a line here because, going from one sherry to two to three to four to five seems kind of continuous. So a line makes more sense to me. Um, and then I can include error bars and we'll just base it on a 95% confidence interval. None of that stuff really matters that much. Again, this is not something you have to do. It's something I like to do because um, it helps me to visualize what the data look like and when I go back to explain it to people. We're going to skip post hoc. Post hoc is actually only if you have a between subjects factor. And let's go to EM means. Come on, thing. I'm going to move Sherry over here and just say compare main effects. We don't really actually need to do that. Let's not compare main effects because we're using contrast, but there are a few canned post hoc tests like LSD and Bonferroni and SIDAC for repeated measures, but let's not do any of that. Our contrasts will tell us how these things differ. And then we'll hit continue. And then let's check on options too. Let's see what's in here. We don't need a homogeneity test because we don't have a between subjects factor. But let's run descriptive statistics and estimates of effect size. Okay, descriptives and estimates of effect size, and then we'll click continue, and we're good to go. So I'm going to hit OK. And you can see that we've got an output that pops up. It tells you what each of your levels of the independent variable are. You get descriptive statistics, and then you get a bunch of stuff that you don't need. There's so many things in here that really don't make a lot of sense. Um, but yeah, I don't know. What does this look like? Does this look like a line to you all or cubic, quadratic? I don't know. We didn't run that kind of contrast, so we'll never know, but maybe we could check on that on the back end here. So I'm going to stop sharing just for a second and go over to our Word document. So here you can see our write-up, and I'm just going to go through this piece by piece. The first thing you always want to do is you always want to check your assumptions. So you tell us about our tests that we're doing. So we just did this repeated measures ANOVA. Um, and I'm saying that the assumption of sphericity was not violated. Okay, why? Well, let's scroll down. Let's zoom in. The first thing I look at anytime I do a repeated measures ANOVA is Mockley's test of sphericity. And look at that p-value, 0.052. Now, I know you might really want to say that that's trending towards significance, but that is not a thing in our world. If it was 0.05 or less, we would go, oops, we violated the assumption of sphericity. But here we did not violate that assumption. Okay. So, what if we had? If we had, let's say if this was 0.049, if we had, we would look at the greenhouse geyser estimate, and if it was less than 0.75, which it is, you'd use the greenhouse geyser row. If that estimate is bigger than or equal to 0.75, we use the Hein-Felt row. Okay. Um, and then you report the epsilon that you would use. Okay. So hypothetically speaking, if this p-value was 0.049, we would use greenhouse geyser. Okay. The reason why is because greenhouse geyser is less than 0.75. Okay. If this were more, then we would use the Hein-Felt. And the way that you report your epsilon is like so. And friends, you can feel free to copy paste these into your outputs that you put together for your assignment 8. You can just copy paste them into Word, and it should go through just fine. Okay.
Can I repeat that to make sure I
Yeah.
understand? Okay, so if it is significant and you violate the assumption of sphericity, you
Uh-huh.
then go to look at your greenhouse geyser number, and if it's less than 0.75, you use that. If
Yep.
it's over 0.75, you use the Hun-Felt.
Yes. Yes. So hypothetically speaking, if we did violate this assumption, I've got an example report down here. So we chose the greenhouse geyser, and then you report your epsilon. Okay. But of course, we don't do this part. And in fact, if you go up to the write-up, it just stops right there. So no correction of degrees of freedom was applied. So I'm just showing you how you would use this in that circumstance, but we don't, it's not appropriate for us here. The next thing that you see is that there was a large significant effect of sharing. Okay. Then you see a report of an F value, P value, and then eta squared. Okay, where does this come from? Now, this is where some folks get a little bit mixed up because there's a lot of different outputs and you have to know which ones to look for. The one that I'm pulling this from is called Test of Within Subjects Effects. And as you can see, it has 4 separate rows of analyses. All right. So, had we violated the assumption, we would use greenhouse geyser because that's what our epsilon told us to do. And we would report our degrees of freedom like so. We'd use those rows. So this is the IV row and this is the error row. But instead, we're going to use sphericity assumed. So we've got 4 degrees of freedom in the independent variable. That makes sense, right? Because we've got 5 levels of the independent variable. K minus 1 in this case is 4. And then for sphericity assumed, we have 32 degrees of freedom in the error. Okay. So basically, we're just ignoring all this other junk here, unless it says sphericity assumed. It's just repeating the table by correcting degrees of freedom. Okay. So all that we really need to know is that our F value is enormous, 28 or 29.84. P-value is less than 0.001. And then partial eta square is 0.79. So you can see we write this up just like we've written up every other uh, F value in previous instances of this. Is it making sense how we navigate through this table? Good. So if let's say that we had, just for example's sake, greenhouse geyser, nothing would really change, right? Because the F value is the same and the P value is the same and the partial eta square is the same, but here's what would change. You see where I'm getting that from? Right here. Okay. So I got 1.997 for my degrees of freedom and then 15.975 for my degrees of freedom in the error. So this is if we had used greenhouse geyser instead. I'm going to pause there just to see if there's any questions about where any of these are coming from. This is always my biggest feedback when I'm a reviewer on a manuscript and people compute a repeated measures ANOVA. They'll be showing these corrected degrees of freedom, and I'm like, hold up, you never showed me Mockley's test of sphericity. So, how do I know you're making the right decision here? So you got to walk me through a little bit more of your decision-making process. So even expert researchers forget to, tell us the whole story that they're required to by APA standards. But we're going to keep this as 4 and 32 because sphericity is assumed. All right. So as you can see, that's already posted in our output here. And this here is just your door. If you open up this door, it means that some of your means are different. We don't know which ones. It's not going to tell us that. So this is where we go to our contrast. Our contrast that we chose was a repeated contrast. So you can see here, we start talking about this. We decompose this effect with a repeated contrast. So what do repeated contrasts do? It takes level 1 and compares it to level 2. Then it takes level 2 and compares it to level 3. Then it goes level 3 versus level 4, and then level 4 versus level 5. Okay. And you might be wondering to yourself, well, I gotta know if level 1 is different from 3 and 4 and all that. But you really don't. I mean, if this is the contrast you chose because it made sense for you in theory, this is what you go with. And the benefit of this is there are one, two, three, four comparisons. Had we done a post hoc, we would have had 10 comparisons. So we're cutting down the number of comparisons that we needed by 60%. That's pretty amazing. We're not going to be inflating type 1 error in a way that's unnecessary. So let's go ahead and start looking at these comparisons. So first things first, we compared one sherry to two sherries. And I've got our means and standard deviations for one sherry and two sherries here. Uh-oh, looks like a typo. That standard deviation can't be 233. I bet it's 2.33, but let's go check. Um, so one versus two sherries. Let's go down to our means and standard deviations. Yep, okay. So for one sherry, it took us 11.33 minutes, our elves, to deliver the presents. And then after two sherries, it was 13.78. Okay. Now the question is, are these different, statistically different from each other? So what we're saying is that they were not statistically different. And I'm reporting an F value. So where did I get this F value from? You get these F values from this table called Test of Within Subjects Contrasts. Now, hang with me here. This has four rows too, but that's only by chance, or four rows of an IV's effect and four rows of an error effect. That's really only by chance with the contrast that we chose here. So you can see the first one's comparing level 1 and level 2. It has degrees of freedom in the IV, and then it has degrees of freedom in the error. It gives you an F value for that row and a corresponding P value. So as you can see, level 1 and level 2 are not different. Or in other words, if your elves have one sherry, you can go ahead and let them have two because it's not going to affect their present delivery time. The difference between 13 minutes and 11 minutes is non-significant. Okay, now let's compare 3 to 2. So we see, but those who drank 3 sherries, oh, they had a mean of 23 minutes. Okay, that's getting up there. Had a longer present delivery time than elves who drank 2. Why does that only say 12? Oh, because I thought that was the mean. Yeah, we've already reported the mean, and that would insult your reader's intelligence. Maybe we should assume that our readers have COVID and they take a little longer to process information because they're cognitively exhausted right now. Um, no, that's our F value. So where did I get this F value from? Let's scroll down. Whoop, a little bit more. Right here, 2 versus 3. It has an F value of 12.31, and it is significant at p.008. All right. So this tells us that 3 is different from 2. And to figure out which one takes longer, we just look at the means. Okay. Well, 3 sherries takes longer. Okay, so let's revisit our story here. If your elves have one sherry, it's okay to let them have two, right? Because that's not significantly different. But if make sure they don't have three, because that is going to significantly increase their present delivery time. Okay. I really appreciate one of you sharing your video to see that there is nodding going along.
You have a question. So
Yeah.
if we go to the row where it says F, the degrees freedom, 1 and 8. Oh, go back up. Sorry, in the text. Um, yeah, and then the p value, yeah, right
Oh,
there, 0.01. Is that correct? Or are we supposed to report from the 0.008?
no, that's you're right. That needs to be 0.008. I just fixed it on here. So now I need to call this file updated again. Thanks, Paige. That really helps. Two more comparisons left. 3 and 4 sherries. Okay. I've got my mean for 4 sherries. So right now we're comparing 26.44 to 23.33. And we say that these means did not differ in present delivery time. Okay, that's good. All right, so let's say they sneak a third drink. Well, you might as well let them have a fourth because it's not going to make a difference in their present delivery time. Okay. maybe they'll be happier or something like that. But you can see 3 versus 4 is not different. Okay. And again, I got those means from down here. Okay, last one. Comparing 4 to 5. 5 Sherry's, the present delivery time was 39.33 minutes. You can see here when you compare 4 to 5 that it was statistically significant. So we know that 5 is more than 4 in terms of present delivery time. And the way that I wrote that up goes like so. 5 Sherry's had a longer present delivery time than 4 Sherry's. Okay. And I'm saying that one is P is equal to 0.001. Let me see if that's right. That doesn't seem right. No, that's 0.013. Where am I getting these P values from? I didn't have COVID when I made this file. So to sit here and say that, this is a brain fog would be incorrect. And I hope that increases trust, because I could have just lied to you, but there's no benefit in doing that. Okay. So what's the main takeaway here? Uh, the main takeaway for me is, all right, so if I'm trying to corral these elves, um, once they've had one drink, it's okay to let them have two, but don't let them get up to three. But then if they do have three, four is okay. Um, but five is problematic. I mean, we're almost at 3/4 of an hour present delivery time when we were under 15 minutes with only one or two sherries. So, I mean, these are extremely large effects on these elves. How we doing, everybody? Seeing where these come from? Okay. So, yeah, let's real quick just run it with a polynomial so I can show you what kinds of output we get. Um, so here I've got my SPSS pulled up again, and I'm just going to go back to where I was before. You don't have to do this along with me if you don't want. I just wanted to show you how to do the polynomial. And I'm going to go back to repeated measures and keep everything set up the same way as it was before. But here under contrasts, I'm going to change repeated to polynomial and go ahead and run it. Um, and let's see what we end up with for our contrast. So um, you'll love this. Everything else is going to be the same. The means don't change when you change your contrast. Um, the omnibus F-test doesn't change. None of that stuff changes. But what does change is the test of within subjects contrasts. So let me paste this into the Word document. So come on, thing. Paste it down here. Really? Okay.
I think I
So say it again.
think it's in there already at the bottom on the updated.
Huh. At the bottom on the updated. All right. What a what a brilliant guy I am here. So this one's pretty easy. And in fact, The less I have to explain, the happier I am. I hate nuance because that's when people are like, I don't want to publish your paper. And we've got a nice, clean linear effect here, which would be interpreted a little bit differently than how we interpreted the repeated contrast. Here, I'd say this is a linear effect. That means that as the number of sherries increases, the number of minutes to deliver the presents increases. We don't have that level of nuance that we had with the repeated contrast. Okay. Yeah, I know the fourth order effect is close, but it's not significant. So here we're taking the most complex analysis. And like a pro, it looks like I reported this already. Um, and check it out. That's so much easier to report than what we just went through. Um, we still want our means and standard deviations, though, so I put them in a table here. That might be something you choose to do. Um,
So in this example, if linear was not significant, but all the other numbers were the same, the next one we would jump to was order four because that's
uh,
next. It.
what this would mean if none of these were significant, it would just be like saying there's no differences between your means. So you wouldn't choose any of them. You would just
Yeah. Okay.
say that I've got a really poor model of this data. My omnibus test was significant, but after that, like we couldn't find any rhyme or reason to why the data looked this way. Um, Also, friends, just so you can peek through these, Helmert contrasts can be done. Um, Basically, we just go through the steps we just went through, and we ask, okay, are these we change from polynomial to Helmert, and what this does is it goes group by group and compares to the mean of all the groups that follow. So, is one sherry different than the average of two, three, four, and five? That's what this is asking. And the answer is yes. Is two different than the average of three, four, and five? Yes. Is three different from the average of four and five? Yes. And then is four different from the average of five? Yes. And interestingly, we actually get the exact same values here for four versus five as we did when we did the repeated contrast because it's the exact same comparison. Okay. I've got little write-ups below them, um, just to give you a sense of what that would look like. If you had to do this, wink, wink, nudge, nudge on assignment 8, the chances of you being asked to do a repeated, Helmert, and polynomial contrast are probably going to be pretty high. I'm not giving anything away because the assignment's already posted. I know we have about 5 minutes, and Aspelmeyer's class is going to be beating down the door to get into the room um, here in just a minute. So, um, does anybody have any questions before we go on our week-long break? And
Yeah, I do. For
yeah,
assignment 7, it says like paste SPSS output, but what like SPSS file are we using for the output?
you're going to make that file yourself because the data are provided to you in the assignment. So above each of the problems, you should um, see the data.
Okay.
You got it?
Yeah, I just gotta see if I can do it on my laptop.
Yeah, and you'll notice that some of those groups have different sample sizes than the other, and some of the examples they all have the same sample size. Um, and I would suggest to you that this is me just like dead giveaway tell that I am testing if you understand when you're supposed to run each different type of post hoc test, right? So if you look at them and you're like, oh man, these sample sizes aren't the same, well, you automatically know that's not Tukey time. Because you have to have equal sample sizes to do that. Okay, so we're really testing your conditional logic here. You can do it. Any other questions as we move forward?